Да. Ага. Okay. Okay, it finally works. It finally works. Yes. Okay, so okay, so we went through rules of natural deduction, right? Last 2 weeks, and it remains to us some rules. I think we went through what? Forward and backward reasoning. I think we should be somewhere at this point. Yes. Yes, that's what we did last time. Here, by the way, on it's all visible, right?
Yes.
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 Okay. So you see here at page 18, you actually have the complete list of these rules, because I think what we did so far, we did this introduction of implication, right? Introduction and elimination of implication, and elimination of implication has this traditional name of modus ponens. We talked about this, right? This is what on the right. So again, the idea of these rules, okay, maybe if you forgot a little bit what we are talking about, right? So we are now studying a system of formal rules for propositional logic. So the idea is that we have here variables like a and b. It's like in school algebra, you have x, y, and z, and a and b again, and whatever, right? Except here, this a and b stand for propositions. And proposition is a, say, expression that is evaluated as a true or false, either true or false, right? So linguistically, if I say something like I'm 57 years old, or Andrei Rodin is 57 years old, just to avoid these problems with first person, this is a proposition, right? And if I go, let's start our lecture, this is not a proposition, because if I tell let's do something, it's not that can be true or false, right? It's some different kind of linguistic animal. However, in language, important role are played by propositions. It's also long philosophical discussion whether or not this role of propositions is so exceptional, central or not central. There are different views, but that does not concern us much, right? It's sufficient to say that there are such things as prepositions in, say, language, in a language, and also in our thought and reasoning. And the logic, or at least the kind of logic that we are studying now, it's about propositions. And it has actually two different parts, if you look, elements, this propositional logic. One thing is how to form some kind of complex proposition from given proposition. Sometimes they are referred as atomic. That means that we just consider them as kind of atoms, right? We don't try to analyze them into elements. And that's what we already somehow reviewed, say, right? So we have conjunction, so we have two propositions. Say one is Andrei Rodin is 57 years old, and the other is, say, 2 times 2 is 4. And then you form a conjunction of those two, and it just says that Andrei Rodin is 57 years old, and 2 times 2 is 4, right? And a similar way, you have disjunction, but instead of and, you have or. Okay, and we already discussed how it works in terms of truth table. And we also have an implication, which is more bizarre in some example. For example, if I say, if Untitled is 57 years old, then 2 times 2 is 4 is true as a complex proposition. However, if I put some falsity at this first place and antecedent, it's called antecedent, what is forms the like first element of implication, say if 2 times 2 is 5, then I don't know, I'm a president of Russia or Tsar of Russia or whatever, right? It will be also true. But there is this bizarre stuff which simply simplify that our systems of logic do not fit our, say, natural language, our linguistic intuitions exactly, right? But still, they do some good job for us, and they're kind of mathematically manageable. Okay, this is just generality. So first, say, part of proposition logic is what I just said, how to build more complex propositions from some simpler propositions, right? We can use conjunction, disjunction, implication, and also negation, right? We may negate a proposition. It's not the case that 2 times 2 is 5, for example, right? So we have this negation. But another, or the other maybe important part is about inference, right? And that's something probably more important, no, at least not less important, because it's more directly refers to reasoning, right? And when we reason, no, it's again a philosophical question, what exactly is reasoning, right? But we understand reasoning in a, if you like, some sort of restrictive sense. So by reasoning, we understand, first of all, inference. Sometimes that sort of reasoning also is referred to as a deductive reason, right? When we deduce things from some given things, and things are propositions in our case, right? So we have, say, some number of propositions, could be 1, could be more, which are called premises in this context, right? And then we put this horizontal line, and we deduce from this proposition some new propositions, right? No, just this standard case modus ponens. We have 2 propositions above the bar, above this horizontal line. First is A implies B, so it's complex. And then we have just A, and we, according to this rule, we are entitled to infer B, right? Which was not by itself above the line, right? It kind of made part of this implication, but it was not present above the bar as a, say, independent proposition. So that's how we think about reasoning, you see? And then, of course, right, and the system that we are studying, it's called the system of natural deduction. I told you already, invented by Gerhard Gentzen. I gave you some historical details. I don't return to these. And it just consists of number of rules. So there is a number of rules. It's like a little bit like game of chess on this formal level, right? So no, except it's different setting, of course. So the idea, you have these rules, and they are, say, all listed there. And already we studied them, part of them, and now actually I'm going to discuss with you the remaining part. Okay, and so you kind of feed these rules with some assumptions, and you infer some new propositions, right? And that's how we think about reasoning. And now there are at least 2 kind of questions, if you like, epistemological, but they are also logical questions, you know. Logic is a discipline which is say, very close to philosophy, epistemology. Epistemology is a part of philosophy, I recall you, which has to do with knowledge, okay, or sometimes also called theory of knowledge, right? So first question is what you actually put there upstairs, right? What you put as assumptions. And the answer is that you may put different things. These assumptions may have different, as we call it in philosophy, epistemological status, but that means that they are kind of known in different ways. They could be mere, say, hypothesis. You kind of hypothesize something, right? Say it's kind of possible, true, and then you see what follows, yeah, what you can infer from that. Or in some other cases, when you may want to use some assumptions which are somehow self-evident, right? Which somehow which you consider as generally known, okay? And those are referred to as axioms, по-русски аксиомы. But again, when we're doing this formal logic, we actually may, postpone this question, not really discuss whether these assumptions are hypotheses or axioms, or sometimes just we say assumptions or even conventions. It's all different kind of epistemic status, and we are now not very much interested in this issue of epistemic status, and just we're looking what follows from what. That's our concern, okay? But then another very important question, of course, is what justify these rules, right? I give you those rules. I say that those are rules of the correct reasoning, right? And recall again in the very beginning of our course when we discussed what is logic about, right? What is a character of logic as a discipline? I told you that it's at least partly normative discipline, right? It does not simply describe how people really reason, because they can make all kinds of errors, or even some intended errors if they want just to trick someone, but it provides kind of norm. So I'm going to say that if your reasoning just complies with these rules, if it follows those rules, then it's good, it's okay, right? But then of course you may ask, but how you know that? How you judge what is good and what is bad, right? Why should we believe it? And then again, that's of course a long philosophical discussion, and again, I cannot say much about that in this course, except that in some cases, like say modus ponens, it looks intuitive, plausible, and so forth. But actually today we are going to discuss a rule which is, say, more controversial than others. And then, if you like, our logic is going to split. That's this so-called reductio ad absurdum. По-русски это приведение к абсурду, or reducing to nonsense, if we try to translate this Latin expression into English, into modern English. All right. So I'll come to this a bit later today, okay? And we'll see. So our logic is going to split to a version which does apply this rule, right? Which does consider this rule as a valid rule of inference, and another version of, say, logic or system of logic which does not accept that rule, that just somehow consider this rule as a wrong rule, which one should not follow, and then it becomes a different system of reasoning, and that's real, right. And then there are again different attitudes. Some people would really argue whether this rule is good or bad, but some other people, and probably the majority, at least today, they would take more kind of technical attitude and say, okay, let's see what we can do with one version of your logic and what we can do with another version, the other version of your logic, right? Then we maybe compare these things, but at least we keep control, right? We keep things under the control of reasoning. So again, it is, of course, a philosophical question with interesting philosophical argument, like pro and contra this rule, but there is also a lot of more technical, say, logical contents, logical details. We just explore these different systems with this rule and without this rule, and kind of relationships between these, and so on and so forth. So we'll come to this today. We already have a time for that. So I think, just correct me if mistaken, that we stopped. So we discussed negation, right? How we may reduce a certain proposition A to contradiction, and that gives us not A. So that gives us, allows us to introduce negation, and actually with this introduction we discharge or cancel this hypothesis. That means that our reasoning, since we made this step, right, our reasoning no longer depends on this A as an assumption, right? We kind of transformed it into negation, okay? And we may also introduce negation. No, that was introduction of negation, right? So we start with hypothesis, we come to contradiction. That's how we introduce negation. So it's a rule for introducing negation. However, we may also eliminate negation, and that's means that we have two assumptions, like not A, and we deduce contradiction, and this is a special constant in our language. We have a special constant for truth, which is not quite the same thing as a just truth value, and for that reason, it's sometimes also called by a Latin name like verum, which is truth in Latin language, right? And this thing is called falsum, which means like falsity, false in also in Latin language. Okay, and here this is where we stopped last time, right? And we stopped also a bit earlier because there was also the seminar. Yeah, by the way, давайте я по-русски скажу. Кстати, ну вот уже там 2 раза, видите, я отвлекался на семинары, но можем, кстати, тоже обсудить, кто там что услышал и послушал, но, в принципе, я готов, смотрите, какое дополнительное занятие делать, да, мы там уже, вот, можно сказать, 2 пары пропустили, так что можно найти какой-нибудь день, ну или там ближе уже к экзамену, чтобы я еще вам провел одно дополнительное занятие. Ну, может быть, знаете, по моему опыту это имеет смысл в таком режиме вот ничего-то там нового рассказывать о подготовке к экзамену, да, что когда вот там ближе уже время начнет не хватать, поджимать, мы просто я сделаю, ну, как бы занятие, где мы там еще раз по всему пробежимся, вы там позадаете вопросы, кто что не понял, вот я предлагаю так сделать. Но если у вас, так сказать, другие идеи, пожалуйста.
Было бы чудесно. Окей.
Давайте так сделаем. Okay, so now we just looking into next set of rules, and that's time for disjunction. Okay. So you see, we have 2 rules for introducing disjunction, which differ actually only syntactically, right? So semantically, so to speak, is the same thing. If we have some preposition A, we may form a disjunction A or something else, whatever other preposition. right? And you see, it's not like conjunction. In conjunction, we had to have A and B, like two assumptions or two premises in order to introduce conjunction, right? However, we had two elimination rule. And again, this difference is syntactic in the sense that we know semantically that this is symmetric, right? If I say A and B is the same thing as B and A. However, since we are now talking about syntax, basically, right? Syntactically, it's different because here we eliminate, what we deduce is a left conjunct, right? Left term of conjunction. So we infer A, and here's the right term. So that's B. And now with disjunction, it's not like this, right? We may introduce things. Is it clear why or it's not clear? No. If I ask you to justify this rule, just to say something in defense of this rule, of course it's informal procedure, right? It's not like a mathematical question, but probably you may just say some words explaining why this rule is valid rule. Вот, кстати, тоже я вот по-русски, по-английски вот мы скажем это valid rule, да? По-русски у нас здесь вот как-то терминология не очень устоялась, как мы скажем, вот правильное правило, да, валидное. Потому что вот если там некоторые начинают говорить как бы истинное правило, но это вот истина, это не про истину, да, это то, что, ну, корректное правило, может быть, так можно сказать по-русски. Okay. По-английски это довольно устойчивое, это validity of rules. Okay. So if I ask someone to validate, to explain why it works like that, not just using, of course, linguistic intuitions, nothing else. Right. You may also probably use these truth tables, what you learned about disjunction, but I rather ask you not for this kind of formal, but rather just why this rule is a valid rule on the basis of what you know linguistically about how this disjunction works, right? How this little word or works. So what you would say to justify, say, this first introduction rule. No, it's very informal. You see, it's not like I ask you to prove a theorem or something, right? It's just blah blah. But you should also do this, and as a, you know, one who teaches logic should do this, right? What you would say, and that's also, I think, good for kind of understanding this rule, right? So how you would justify it. Yes, please.
I have
Mhm.
kind of stupid example, but as far as I
Yeah.
know, when we Google something,
I'm
and-
sorry, who is talking?
Vasilisa,
Vasilisa, good. Okay, okay.
and we write something like, okay, Google, please search tigers or lions, for instance, just and the system will be seeking for articles both about tigers and lions, or only about tigers, or only about lions, and we will be satisfied in each of that cases because the junction is
That's
suggested.
interesting. So what? Yeah, it's interesting, but that's true. You are kids of this epoch of Google's.
Yeah,
so
like,
it's at least not this
disjunction can be
important. But
true
but I just did not quite follow you. So I never tried. So what you're saying, if I understand it correctly, so if you if you type right on Google on search, I want tigers or I don't
Lions.
know, lions, and then what you say, it gives you what? It gives you both.
It can give me both, but it also can give me articles only about tigers or only about
But
lions.
it's an important question. But if I type, say, tigers and lions, do you think would be different? Yeah, we may try, by the way. Yeah.
Yeah, I guess it would be different.
Are you sure? I'm
In
not
that
sure.
case, he Google must search only for articles about both when we use and.
But
As far as I know, I'm not that good in searching.
But let me just try. Okay, I can.
Okay.
Yeah, it's good. That's very, very good and interesting point you're making. Let me. Okay, I think this one. Okay, tigers or lions. Yeah, it comes just first. Okay. Tiger. You see what?
Probably we need to not use the word or, but the symbol.
Even symbol. I don't know exactly how it's. I can try this. I can try latex symbol. Wait, no. No, sorry. Wait. I think it's called V.
We discussed it at school, but I can't.
Really?
Yes, but I can't properly remember what.
I don't know what, but
do?
it shows me Psy football club. You see? And so what should I? But okay, but let me say just and see. Yeah. No, I don't. No, what I know. Okay, you should of course talk with people who know more about computer science and Google in particular than I. However, what I know is this: that actually these logical functions, they are not implemented in Google's search. You see, and that's something interesting for computer science, because you see the early attempt of, say, artificial intelligence, right, broadly conceived, that started, say, in 50s. In 53, 57, there were a couple of articles by was a guy McCarthy, I forgot his first name, but kind of father of artificial intelligence. And so what these people tried, and today this old-fashioned artificial intelligence is referred to as sometimes symbolic or logical artificial intelligence. Okay, and that's so these people had this idea that they have some, say, system of logic like this one that we are studying, right? And so they start with system of logic, okay, and then they find the ways to implement it on computer, which is, by the way, is not at all immediate, right? So they, I don't know exactly, they took natural deduction or maybe something else. However, that was the idea, that somehow if you want to teach computer to reason somehow, right, like a human or with a human, whatever. So what you should do is kind of implement some formal, how say, some formal scheme of reasoning, right? And what is formal scheme of reasoning? It's logic, okay? So you should, do some logical calculus like natural deduction, and then think how to implement it in computer. That means how to basically write a computer code, write a program that somehow implements what we do in logic, something like this, okay? And that's were all early attempts. However, a really, what some people call a revolution in artificial intelligence actually came from very different direction. You see, that's something interesting and not, I think, not quite yet understood even. And by the way, Google probably was one of the first. Google, it's not exactly artificial intelligence, you know. However, the same, what I'm saying, applies just to searching engines also, right? Because a kind of old-fashioned idea of searching engine is this, that you should somehow classify all data, right? You should have a system that, no, you know, like in a big library, you should say, here you have books for cooking, here you have books for whatever, mathematics, there in philosophy, and then if you need to find something, you type something like, I want a book of, I don't know, cooking philosophy. And then, you know, it looks for, say, book which is somehow both about cooking and philosophy. That again, using this logical scheme behind it, okay? However, a real breakthrough with Google, there were some earlier attempts before Google in Russia was this Rambler rather early, but it's not important. But important that they were not based on this idea at all, and they were rather, no, it's if we're talking about Google, there is no full understanding because, you know, those algorithms are even commercial. They are not all open source, so kind of commercial secret. However, of course, we understand general principles, but general principles rather by association of words. So it's, no, roughly speaking, does not use logic in any explicit form. And later came what is known as machine learning, like deep learning. I think you heard about this, right? And again, and that's how, for example, like chess computer or computer who win in the game of Go, which is actually more complicated, computationally speaking, than chess. So they all use this machine learning, which again, roughly by some association, okay, I'm not expert in that, and second, I have no time to talk about this. However, it's not about logic, right? And already more recently, people still become to think how to combine, if you like, right? This kind of logical approach and this machine learning approach. But what I know certainly about Google, because that's dates still to some time, which I understand better, that it's not based on logic. So I don't think that's really, it marks this little word "and" as a, say, logical concept. It does treat it as a logical concept, you see. And for tigers and lions, or tigers or lions, it gives more or less the same thing. Or
Sorry.
Yeah, no?
It would work if you type "or" in capital letters.
Really?
Yeah.
Okay.
Or if you want to find something only, for example, Nikola Tesla, and you want to find only Tesla, you need type Nikola minus Tesla, and then it would find
okay.
brand of cars.
But
So
can you see my screen? No? With Google, no?
It is stopped on only tiger so maybe.
So now I type tigers or with capitals, lions, and again, okay, I have lion Wikipedia for lion, and what? And I have nothing for.
Probably just not the best example, because there are many articles about both lions and tigers. But if we take some topics that are not that connected.
Okay, give one.
Let's
Okay.
say Tesla and
Tesla.
lines.
Okay, Tesla or lines, right?
Yes.
Okay. Tesla, electric cars, blah, blah. No, I don't know. Maybe you are right. I don't know this. Probably they try to somehow implement this logic. Probably I should mark somehow this or, not just with capitals, but with some other symbols. No? Yeah, we should read about it. Perhaps they introduced, after all, some logical functions like this one. But what I do know that the real power of Google, it does come from logic. That's I'm quite sure that's. Except that now many people really think how to implement logic, because what you do without logic, it makes things somehow very effective sometimes, right? But also very unstable, and you can say unreliable. So you know the same with machine learning when, for example, you know these experiments there, you have a, I don't know, picture of dog and cat, and you teach your system to recognize, to distinguish between cats and dogs rather effectively. However, you can easily trick it. You can show a picture which human eye immediately recognizes like something else, and this kind of machine learned system, right, would be tricked, would say this is a dog, right? When and that's as people think. So we may still use logic, but not really as a basis, right? But it's kind of stabilizing device. No, it's like more or less in a real life, even without computers, we just talk, we give arguments, this and that, and we use logic to normalize it, right? It's not that we just learn language with logic, right? We learn and teach logic much later than we just learn language, right? And even later than we learn to make some sort of arguments, or say even mathematical arguments, right? And only after that we have this kind of reflection, how we really argue, what are general rules for reasoning. That comes much later. Okay, so okay, let's. No, I think that's a really interesting topic, which connects us to computer science, to everything. But okay, but actually, I just asked to. So Google example, I'm not sure it's really clarifying. So no, what I expected asking you to give some justification for disjunction was something like a linguistic argument, right? So I'm trying to explain to someone how disjunction works, right? And why our understanding how it works, it's really kind of captured by this rule. That's, I don't know, maybe someone else may try, but it's good point with Google. Yeah, thank you. Yeah. Maybe someone else may try just to explain why we may really infer from just any proposition A, we may infer proposition A or B, where B is just any other proposition. Yeah, someone. I'm pretty sure someone tries to tell something, but I can hardly hear. Oh yeah, sorry, I should go back to my. No, okay, let me try myself if nobody volunteer. So what we understand by or logical, right? So we understand something which, which adds up to what we already know. No, let me try in terms of knowledge, right? So suppose we know A, right? We know then, say 2 times 2 is 4, something like this, right? And then this disjunction serves just as this specific kind of connective, that we may kind of attach to this knowledge, say some other knowledge, like B, without being committed to this, right? Without being committed to B. So if I'm saying A or B, that means that either I know A or I know B or I know both. That's how my notion of disjunction, or that I express in language by this little word or, that's how it works, okay? But now we have A as an assumption, okay? So we do know A, and then we don't know B, right? However, it's still A or B will be valid. Also, just knowledge of A is sufficient for knowing A or B, even if we don't know B. No, roughly, that's what I can say about this, okay? So I have this formal rule and I have this kind of informal linguistic explanation in terms of knowledge. We may probably give another different linguistic explanation, not in terms of knowledge, but say in terms of truth and falsity. Yeah, but that's how more or less it works. Okay, but just notice again that we have actually two such rules. Even, of course, they are not really distinguished on the semantic level when we try to explain them. However, syntactically or symbolically, if you like, they are different, right? Because again, here we kind of adjunct this other term here to the right and there to the left. So it's syntactically speaking, not the same rule. Even semantically, we may say just the same, or saying A or B is the same as B or A. Okay, that's about introduction. But you see, elimination actually is a bit more involved. It's a bit more involved. We'll see this on examples, and probably I go. No, okay. Let's see the rules, and then I go back in our textbook to go through some examples. So the rule is this: that okay, we have this disjunction given as one of our premises, okay, and now we want to do something to eliminate this disjunction. And so how we do this? And that's actually what is called reasoning by cases. We say, okay, let's see what happens if A is true, right? A. And then we reason, we do something. And I recall you that these dots actually refer to reasoning according to the same rule. If you like, it's a description, it's kind of self-referential. You see, we have a kind of description of this rule, which actually refers implicitly to reasoning, which already may involve this very rule. That's a little bit bizarre. No, however, in this context, is fine. If we want to make things computational, is not fine. Actually, we should somehow to do something more precise than just putting these dots. However, the idea is this: that we can, okay, let's A is the case, okay, and then we reasoning and infer C, and then we say, okay, and now let's be the case, okay, and we reasoning again, and it would be some different reasoning, but we come to the same C, right? And at that point, we may naturally just infer the C and discharge all those hypotheses, right? So we kind of infer C from disjunction. No, okay, let's see on some examples how it works, because that's a bit abstract how I describe it in that way. Derivations and natural deduction. A negation proved by contradiction. Yeah, here we are. That was a bit different. That okay, here we are. Yeah, let's see. Look, they are trying to give examples again from our story about Alice's husband. Remember this family murder, and right, and that's no. So remember that was just element of our solution, and I think. I forgot who actually gave us excellent solution. One of you certainly did. And then, right, we just had to have this different versions, right? Then we knew somehow that I forgot already that what woman was in the bar, not woman. But anyway, we had to consider these two, say, possibilities, or logically speaking, hypotheses, that either Alice's husband was in the bar or Alice was in the bar, right? It was, we were told that there was just a single person in the bar who was not a murderer, I think, right? Something like this, right? No, anyway, we had these two options. Right, and then but then somehow we also knew from different sources that actually husband was not in the bar. Sorry, yeah, but this is more simplified. Sorry, I should see. Sorry, I would see before that. No, these I think are easy, right? This introduction, so I will not stop. Right, let's see this. Either Alice's brother was in the bar or Alice's son was in the bar, okay? So we had these two possibilities, say, only apparently compatible with our, say, conditions, with our data. But after all, we'll see that only one is compatible, but it looked like we had to consider both these possibilities, but then we consider them just one by one. Remember, right? So first we just symbolize as a disjunction, right? So A is that Alice's brother was in the bar, and B is that Alice's son was in the bar. Okay, and they are connected by disjunction. So we have this disjunction as our premise, okay? But then we consider both these cases separately, and we start with case A, so that Alice's brother was in the bar, and then, okay, there were some reasons I don't come back to them, but we come that since Alice's brother was in the bar, her husband was on the beach. Okay, and that means that we took our A and then we reasoned, and now we just skip this reasoning and just look into conclusion. And so C is that husband was on the beach. Okay, here we have C, and that was our first option. Okay, here we stop, take a while, and then we consider the second option. And second option was that son was in the bar, and again the reason, and again come to the same conclusion. You see? So, so if you like, we did not actually resolve. We did not, did not determine. We still don't know who was in the bar. It was Alice's brother or Alice's son, or maybe even both of them. We only have this disjunction. However, we manage just to using this first hypothesis and again, generally speaking, disjunction is not exclusive disjunction, right? So by saying A or B, it comprises the case that A and B, right? So it comprises its disjunction is true also when A is true and B is true. Okay, but anyway, we just consider these cases just one by one. So take first case and derive our C, husband was on the beach, and then consider the other case and derive the same thing, right? And now what we can say that what follows from this disjunction is our conclusion. So it's the same in both cases, in first case and in the second case. You see, no, it also, I probably should give you more concrete example. However, it happens also in mathematics. For example, no, okay, I just will not give you concrete theorem, but say something about triangles, right? You may have some theorem about triangles, which says something general, whatever that say, intersection of medians, the point of intersection is the same as, not, it's not the same, what? No, okay, just a theorem that says that sum of internal angles is a two right angle. I think we looked into this theorem, right? But in many cases like this, to prove the theorem, you should consider separately the case when triangle has only acute angles, right? It's like, как по-русски называют, треугольные треугольники в школе, так. And the case when triangle has obtuse angle, one obtuse angle, or separately probably also the case when triangle has a right angle, okay? And it may happen not actually in case of this theorem, but okay, in some other cases that I may look for next time. You geometrically somehow you prove these cases differently because you have different geometrical construction and so on. But you prove the same thing. You prove the same thing. You just say it works for such triangles, for these triangles, and for this. So it actually works for all triangles. Yeah, that's how this pattern of reasoning works. Okay. Maybe some questions about this. Yeah, they actually introduced us here. You see one more rule which was not in this list below that I just showed you, right? Which basically all rules of natural deduction, and this extra rule is is also very natural. So it has a or B as one assumption. It has not A as the other assumption. There is two in total, two assumptions, two premises, and then you may conclude B, right? No, again, it's I think quite well corresponds to the intuition how we understood disjunction. So first, say, let me again explain in terms of knowledge. So somehow you do know that either A or B, but then you know that not A, and then you conclude that B, right? So you know B, right? But question why this rule is not on this list of say basic rules of natural deduction, even if it's quite obviously valid rule, is that actually this list is not a list of all valid rules. Okay, it's a kind of minimal list of valid rules, such that all other valid rules may be derived from this. And derived in that case means not that you derive conclusion from premises, but it means that you may analyze this rule into several steps, okay, kind of several elementary steps, and we are going to do this actually a bit later when we complete. And these steps are going to be this kind of basic rules, you see. So you have this short list of basic rules, but you may, roughly speaking, combine them in different ways, and that gives you new rules. If you just look what in your premises and what is your conclusion, you may always kind of skip what is in between, right, and consider this new thing as a new rule. Okay, that's the idea, and the idea of this basic rule just make them minimal, such that any other valid rules is obtainable or derivable, if you like, from these basic rules. And of course, there is more than one option. You may choose as your basic rules actually different sets of rules and still obtain the same deductive system. Okay, yeah. So they say we will not take this to be fundamental rules. So they call it. I told basic. They call them fundamental, but that's the same thing. Basic and fundamental. Okay. All right. So, no, okay, let me proceed, and then we come to more examples. It probably will become clear, but if you have any question now, just interrupt me, ask me, okay? So we finished. When we are making the break, I already a little bit lost. So we started. So now it's 6. So normally it's break in 10 minutes, right? Yeah, we may probably make it in 15 minutes. Okay. Okay, so now let us move a bit further to next set of rules, which are now for equivalence. And equivalence is actually kind of double, it's an implication in double sense, right? In writing, it's sometimes written if with double F, which means, is read as if and only if. Who knows how it translates into Russian? If and only if.
Тогда и только тогда.
Да, вот иногда говорят так, если и только если, но такое более, да, в русском языке вот устойчивое выражение, тогда и только тогда, так вот математика. Это вот оно и есть. Да. If and only if, тогда и только тогда. Иногда пишут, но это как-то не очень распространено. Вот. ТТТ. Три раза Т с точечками. Ну вот логики иногда таким пользуются. По-английски вот это if с двумя В довольно распространенно в таких контекстах этим пользуются. Okay. Ну, okay, let's see just some examples. Malice and Alice. I claim that Alice is in the bar if only if Alice's husband is on the beach. To see this, first suppose that Alice is in the bar. Then, blah, blah, we reason, and has Alice's husband is on the beach. You see, that actually works as the introduction of implication. Yeah, remember, right? Let me probably show you. Scroll back and show. Yeah, this one, right? So we have some assumption, and then we reason and obtain, say, some other proposition as conclusion, and that allows us to introduce implication and discharge this antecedent as a hypothesis, right? And now it's basically the same thing, except we do it's then again in the other direction, right? So we begin with this, but then we also proceed the other way around. And that gives us roughly implication from B to A. And these two implications together gives us equivalence, what is called logical equivalence. By the way, I can't remember whether we wrote truth table for equivalence. Is A is equivalent to B. Okay, okay, let's write also truth table. So example is this again. Suppose Alice is in the bar, blah, blah, blah. Hence, Alice's husband is on the beach. Conversely, то есть в обратную сторону, suppose Alice's husband is on the beach. Blah, 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 Alice is in the bar. And that basically means that we proved equivalence. So this is how, this is introduction rule for logical equivalence. We take A in derive B, then take B, derive A, then these things together allows us to introduce equivalence between A and B and discharge both A and B. So it's kind of doubling negation, implication, right? First from the left to the right, and next from the right to the left. And truth table. Right, it's oh, sorry. Okay, if I have A, B, and now I have this A equivalent to B, okay, and here I have true, true, and true, false, and false, true, and false, false. So what is a truth table for equivalence to B? Maybe someone knows. No, okay, I can tell you. So it's true here. It's false there, because those are different, you see. So we have false, we have false, and we have again true. Now, roughly, what equivalence says that A and B always have the same truth value, right? If both are true, they are either both true or both false. So we have truth here and here. And if equivalence is false, that means that we may have A true and B false, and the other way around, A false and B true. So that's true table for equivalence. But now, that's already told you kind of semantical thing, truth tables, right? When we evaluate our proposition with S being true or false. And here we have just deduction rule. So we, in a sense, we don't care about true or false. We just saying that if we infer B from A, and if we also infer A from B, that entitles us to infer equivalence of A and B, and that's even does not. So we may know that A, B are equivalent without knowing either A or B. You see, so if we know equivalence A and B, it does mean that we know A or B. No, it's like with implication, right? We may know implication that A implies B, right, without knowing A and without knowing B. No, in semantic terms, that means that A might be true or false, and B may be true or false, and we might not know. However, we do know implication that A implies B. And the same for equivalence, we might not know whether A is true or B is true. However, we do know after this reasoning that they're equivalent. That they either both true or both false, but not one true and the other false. That's the idea, okay, of equivalence. Sorry, I should right, I can just undo my okay. Okay. Yeah, so we have these introduction rules. Right, and now we come to elimination rules for equivalence. And here is example for, no, okay, I don't know what is better actually pedagogically. First look on informal example and then to formal rule, or the other way around. By the way, maybe you have some opinions, no? What is better pedagogically? First, say informal linguistic example, then formal rule, or just start with formal rule and then illustrate it with linguistic. Maybe it's different for different people. Depends on your somehow habits, intellectual habits, perhaps of your brains or whatever. Yeah. How do you feel? What is better?
Maybe some informal example.
To start with, better, right? And then come. Okay. Is that everybody agrees, or for someone better start with formal?
I agree to start with informal.
With informal. Okay, okay. Interesting. Yeah. No, okay, let's see. So now that was an introduction rule, right? Because we introduced this equivalence. Now how we may eliminate it. Okay, informal example, if you want, is this. Alice is in the bar if and only if Alice's husband is on the beach. That's somehow we deduced earlier. That's going to be our first premise. Second premise is that Alice's husband is on the beach, so we somehow know it for different reasoning. And then we know that Alice is in the bar, right? It's clear. Alice is in the bar if and only if her husband is on the beach. Then suppose we know that husband is on the beach, hence Alice is in the bar. And formally, but formally it's a little bit bizarre because again, you see, we have this syntactic difference, which somehow not felt semantically, or at least in my understanding. Maybe some of you has more sensitivity to, I don't know, to written language, something to. But here again, for similar reason, we have two rules rather than one. No, the idea is always the same. We have two proposition equivalent, and then we know one of these proposition, and so we infer the second. So A is equivalent to B, then A, hence B. However, we may write kind of not quite, I don't know, complementary, symmetrically. Again, A is equivalent to B, but now we know not the left one, but the right one. and then we infer A. And again, syntactically, it's two different rules. Right. So that's how we work. It works. So since we do know that two propositions are equivalent, we may kind of use one to control the other, if I may say this. Okay. So here we use A to control B. Right. And here we use B to control A. And formally speaking, we do eliminate our equivalence as connective. We eliminate in the sense that we have some premises that involve equivalence above the bar and below the bar. We don't have this symbol. That's in that sense we mean. Say we eliminated it. Okay. All right. Mm-hmm. Okay, I think it's no. If you have some questions, please ask me questions. If not, ну, давайте я по-русски. Это, кстати, знаете, вот интересный момент насчет этого формального-неформального. У меня просто сейчас две дочки 7-летние, двойняшки, которые, значит, учатся играть на фортепиано. И вот у них абсолютно по-разному устроено. То есть вот одна девочка, Агата, она вот все, она уже выучила всю вот эту нотную запись, то есть она вся как-то вот у нее через синтаксис, да, через глаза. И потом она играет. А вторая, Аглая, у нее вот все наоборот. Может, это более типично, да, что она так как-то играет со слуха, а вот с этой записью у нее, так сказать, проблемы. Ну вот видите, то есть у кого-то, ну то есть это такая штука, конечно, которая на самом деле должна, наверное, это такой круг, да, это не так, что сначала одно, потом другое, но может быть, действительно, вот есть какая-то разница, что одним проще начать с этого. Может быть, все-таки действительно это, так сказать, более фундаментально, что мы начинаем все-таки с языка, да, мы же язык учим вот как-то в младенчестве, и потом вот какие-то у нас есть примеры, как мы что-то спорим, там что-то доказываем. Потом вот мы немножко учимся математике, и там что-то доказываем. А потом уже, да, вот мы это формально записываем какими-то, так сказать, значками и формулами. Но эти значки и формулы, видите, они тоже помогают как бы сказать, в обратную сторону, да, то есть это не просто это, как сказать, такое абстрактное описание, но это такая вот нормализация, то есть мы действительно можем употреблять это все, чтобы... Ну и в нынешние времена, конечно, вот это все идет через компьютер, но про это я говорю, вот это надо отдельный, в общем-то, курс делать, потому что это все переводится на компьютер, но не по щелчку, понимаете, там вот свои возникают такие разные интересные моменты и проблемы и так далее. Вот, ну давайте тогда сейчас перерыв и вернемся через 20 минут. Okay, shall we resume?
Yes.
Okay. Yeah, okay. Now we are coming to this very interesting, actually, case that I already announced in the beginning of today's class, and which is called proof by contradiction. По-русски, давайте я вам, да, тоже. Вот эта штука называется доказательством от противного. Но на самом деле здесь, вот когда мы говорим доказательство от противного, и даже, мне кажется, вот это английский вариант это не очень исправляет, то могут подразумеваться две разные вещи. Вот смотрите, у нас был случай, сейчас я перейду на английский, но давайте вот эту часть проговорю на русском, когда, ну, случай введения отрицания, да, где у нас там был? Вот, когда мы рассматривали какую-то гипотезу, приводили ее к противоречию, и таким образом мы делали заключение о том, что эта гипотеза ложна. Да? Ну вот такие примеры у нас как раз были хорошие в первой части курса, где мы вот давали примеры математических доказательств. Ну, например, у нас был пример, помните, что мы предполагали, что у стороны диагонали квадрата есть общая мера. Ну, сейчас не буду уточнять, что такое общая мера, но вы помните, да, какой-то, значит, отрезочек, который целое число раз укладывается и в стороне квадрата, и в диагонали квадрата. Вот, и мы доказывали, что такой общей меры нету. Да, ну, мы ставили вопрос сначала, вот, так сказать, как, не как теорему, а как проблему, то есть ее найти, там что-то, так сказать, делали, но потом мы доказали теорему, что на самом деле эта задача, проблема не имеет решения, что какой бы мы метод не использовали, что бы мы ни делали, такой просто общей меры нет. И, ну, сейчас я не буду воспроизводить все это доказательство, но идея была в том, что мы предположили, что такая мера есть. Помните, потом там, так сказать, у нас шло такое рассуждение с конструкциями, мы использовали, там, так сказать, данные другой задачи о том, как удвоить квадрат. Дальше у нас такое шло арифметическое рассуждение, да, про то, что там n квадрат равно 2m квадрат, что вот таких nm не может быть, потому что там с четностью был аргумент. Ну, сейчас не буду все это воспроизводить, но важно то, что вот мы начали с некоторой гипотезы, вот в том примере, что сторона и диагональ квадрата имеют общую меру, и пришли к противоречию. Так? И на основании вот всего этого мы пришли к заключению, что гипотеза ложна. То есть в данном случае, значит, ложно то, что есть общая мера у стороны и диагонали квадрата. Вот. И это, видите, ну тоже можно назвать proof by contradiction, да, то есть у нас здесь существенную роль в нашем рассуждении играло противоречие. Да? Ну и по-русски это тоже, в общем-то, называют там математики рассуждениями от противного. То есть нам нужно было доказать, что общей меры нету, мы предположили противное, что она есть, и пришли к заключению, в конце концов, что ее действительно нету. Да? Вот. Но это не то, что имеется в виду под доказательством от противного, или по-английски proof by contradiction, вот в случае, который вот мы сейчас с вами рассмотрим. Это немножко другое. И вот эту разницу надо понимать, потому что просто вот эти названия proof by contradiction или вот русское название доказательства от противного, они как бы эту разницу вот прячут. То есть вот здесь как раз тот случай, когда нам формальный подход очень важен, потому что на самом деле здесь речь, ну, что-то тут похожее, но на самом деле здесь используется некий дополнительный логический принцип. Ну, давайте тоже начнем. Let's start with the informal example as you advised me, and actually as the authors of this textbook do. Okay? Okay. So first they just refer to these examples that I just came across, right? That we have a hypothesis, Alice's husband was in the bar, and then come to the contradiction, which here is just expressed by what impossible, and then we negate that, right? We say therefore Alice's husband was not in the bar. However, right, and this is something different when we say this. You see, we suppose, for example, that Alice's husband was not on the beach. No, that's the different example, different reason. Okay, then we reason, do something, come to contradiction, and conclude that actually he was on the beach. You see, it looks similar, however, it's essentially different, right? And the difference, no, at that point, I would still look into formal part first and then come to discussion. You see, they discuss it, and okay, I'll give you some example. So the second time is not the same scheme, right? So we start with negation. We start with negation, come to contradiction, and then we introduce, we conclude to not negated thing, right? No, actually, different way to think about this, if you like, actually logically equivalent. Let me again annotate this. Okay, if we just trying to apply to that case this scheme that we used earlier, that is introducing negation, right? So if we do this, so we have this, negation in the beginning to start that, then we reason, then we come to contradiction. And then actually, if we only use this rule above, introducing negation, right? We should conclude that we actually negated our negation. So we have not A, right? And of course, just using some linguistic, again, intuitions, we may say that not A is the same thing as A, right? So we may write that not A is equivalent to A, okay? However, this is an additional principle, right? We did not use this principle earlier, that we may, that one negation cancels the other negation. Of course, we may also kind of justify it using truth tables, if that really works as a justification. Okay, in a truth table for negation, I can remind you, it's also simple. If we have A and here we have not A, right? So we have true for A, and if A is true, not A is false, and if A is false, not A is true, right? And that case, double this canceling of double negation, it works. So if we just substitute not A for A, you see, so basically this negation operator, we may call it mathematically, kind of algebraically, right? So what negation does, it swaps truth and falsity, right? Just if it was true, became false, and was false, became true, right? And so if we negate negation, we come, if I write here, say, double negation, not A, then just using the same truth table, basically I come back to true and to false. And you see, this is equivalence. So I have the same truth values for A and for not A. However, this is additional principle. This is the thing, you see? So it's not justified just by this rule for introducing negation that we already came across above. So it's a new rule. And rather than talking about double negation, but you see it's kind of equivalence, we just introduce a new rule in this form. And here it's called not even introduction or elimination of something. It has a kind of, sui generis, peculiar. It's called reduction ad absurdum, or reductio ad absurdum in Latin. One, that means that we actually discharge our hypothesis again by just using this inference. Yeah, that's what why this little one. Okay, so again, we might not know A, whether A is true or not A is true. We simply take not A, and then we reason and come to absurdity, and that proves us A. So at the end, we do know A. Even at the beginning, we might not know neither A nor not A. That is a certainly new rule. Yeah, it's also is equivalence that we may probably, that's also easy to explain in terms of a proof table, in terms of so-called, no, it's sometimes called law. I already, I think, mentioned it again in the beginning, law of excluded excluded middle. Sometimes it's abbreviated as LEM, L-E-M, and it also has a fancy Latin name, tertium non datur. Tertium means the third, not non datur. Non datur means not given. Yeah. No, roughly the idea is that there is nothing in between true and false, and that's roughly corresponds to what we just discussed about double negation, right? That negation simply switches truth value, right? There is nothing in between. And this law of excluded middle is also written, and that's also equivalent. That's okay. I will not going to prove formally now. It's actually easy in this form, that for every say proposition A, we have A or not A, you see. And now if we think about this A or not A semantically, that is in terms of truth table. So what it says, if A is, say, true, then not A is false, right? But the disjunction is true. But if A is false, then according to this truth table for negation, not A is true, and the disjunction is again true. So this A or not A is true in all cases, right? So it's a tautology, something that is true in for all possible values of A, and it has only two possible values, right? True and false, right? So it's always true. Yeah, but thing is, yeah, and it sounds okay, kind of plausible, right? That's right. If we have A, then if A is true, then not A is false, and the other way around. If A is false, then not A is true. This is always true. However, it's actually disputable. So there are contexts where you may be not happy with this rule, to put it that way, not happy, and just want just not to use this rule. Okay, I will give you two mathematical examples, right? One more say, illustrative, and the other actually. So one example is not really proof, but kind of just illustration, kind of talk about truth values. And second is an argument, is a reasoning which does use this low excluded middle, and which is kind of, you may doubt whether it's really, how say, valid reasoning or not really valid. So that's good, I think. Okay, first example is, okay, I'll probably switch to my desk, okay, because I'm going to write certain things. Sorry, I didn't open it in advance, so I should do it now. Yeah, and that's, I think, interesting. It shows that, after all, logic is not just something that everybody knows anyway, or probably does not really need to know explicitly, because it's, say, controversial, right? We may call it controversial. Something that there are certain reasons to accept and certain other reasons not to accept. And okay, no, yeah, this is my board. Okay, do you see now the board?
Yes.
Okay, yeah, so let's me write it. Again, low, yeah, of excluded middle. Okay, I stop probably my video because then I can write better. Excluded middle, and it's actually equivalent to double negation rule. So whether you say that A or not A is a tautology. So if I'm making truth table, it will be truth for all values of A, right? Obviously, or I say that A is equivalent to, yeah, that by the way may be an exercise. Just try to, and let's discuss it on the next week. It's kind of easy exercise to show that these things are equivalent. Yes, that whether you assume low excluded middle, or you assume this canceling of double negation, or actually, as we do in this more Gensen style, as you explained, right, in form of rule rather than in form of tautology, is also equivalent. Okay, but now let me. So that's exercise for homework. yeah, just show that these things are exercise. Now let me just show examples that somehow can make you doubt that this is a valid rule, or very valid law in that case. Okay, first let's think about decimal expansion of pi. You know this number pi, right? Where that comes from geometry. If you want to calculate length of circle, it's and this is its radio, then this length is 2 pi times this radius r. I think you remember this from geometry, and actually this is important. This is a not only irrational but also transcendental number, so-called transcendental. That means that it's not a root or solution of any polynomial. So you cannot, it's not like square root of 2. We learned, right? And that's, we are going to use in my next example, that square root of 2 is irrational. And this is roughly the same thing as saying there is no common measure of side of diagonal, or side and diagonal of a given square. All right. And irrational means that it is not equal to m to n, so there is no such m and n that it equals to this fraction, right? It's not a whole number, that's clear, but it's not a fraction. But it's in a sense it works with number p, but still it's a solution of equation like x square equals 2, right? This we say this is a solution of this equation, but pi is not solution of any equation. But right, and actually to define this number accurately and actually to prove that it's transcendental, that it's not a solution of equation, it's rather involved mathematics. It was historically it was only the second half of 19th century where people proved that. So you need quite a lot of algebra to prove it. It's not simple. But anyway, what you probably do know about pi, right? Above the geometrical example, that you may kind of calculate it, right? You on some I don't know, calculators, I think it's exist. So you, and what I mean calculate, that is to make decimal approximation. So if I write, I actually remember that far. Yeah, maybe, but you may further. That's I just remember by heart from school. Because if I just take this number without dots, right? This is a fraction, of course. It's like m to n, right? It's expressed in different form. However, we know that actually it's not really pi, right? But then it's only up to certain approximation, right? But then you may calculate more and more and more digits if we do that all in decimal system, and it becomes kind of closer to say real pi. And basically that means that you have a short program, an algorithm that does it. Okay, and then of course there is also kind of computational issues, how to make the best algorithm which works, which gives you largest number of digits in shortest time and using less computer resources, less memory, and okay. But okay, we don't go to that. It's just important to understand that we have kind of infinite, potentially infinite series of these digits, which are computed by certain algorithm, but you may figure out that kind of algorithm. At least some of these arguments, it's not very difficult to figure out. You may, for example, approximate your circle, say with a polygon, right? And then calculate the size, the length, the perimeter of this polygon, and then you see if you divide every side of your polygon by 2, you have kind of another polygon which better approximates your circle, and so on. Yeah, that's just one way to calculate pi. There are others, right? But the important thing that you have roughly a program, an algorithm which computes these digits just one after one, and I don't know exactly. I know that there is a kind of competition between programmers, for example, how much one manages to calculate these things. And frankly, I don't know what is the current score, maybe some matter of millions or something like this. And that's, again, as I say, it depends on your algorithm. So you should invent kind of clever algorithm to calculate more digits within some reasonable time span, say, I don't know, 1 week or something. Right. And moreover, what we also know from, say, arithmetics, that it's not very difficult that to prove that since it's irrational, it's actually there is no repeating pattern. If you're writing, say, 1/3 in this decimal system, right? You obtain something 0, 3, 3, 3, etc. ad infinitum, right? So it will be 3, and actually. For any rational number, so for any number of this form, will be some repeating pattern here. But if you have irrational number and moreover transcendental number, there'll be no repeating pattern. So we no, roughly speaking, that means that we can't really predict which are how this series behaves. You see, we may try to prove, and perhaps some people did try. I don't maybe know all that has been done about this. Some general theorems about this, but still we cannot really answer some very concrete question. For example, we cannot say whether or not there exists in the series, no, say 100 zeros, one after another, right? 100 times. I think it's safe to say that it never happened. So people who really calculated pi never came across such a fragment of this expansion. Expansion это как разложение по-русски. Ну вот в таких по-русски как-то это не называют разложением. Десятичное разложение, но вот по-английски так говорят. Decimal expansion. So important thing, say nobody ever came across, right? Just calculated it. However, there is no general theorem that would tell us that it's impossible, that it just never happens. Whatever, however long you calculate that, it would never happen. There is no such argument, there is no such theory, okay? Right. However, now let's consider, say, proposition. Okay, we call propositions like A, and the proposition A will be as follows, that the decimal expansion function of pi, yes, contains 100 zeros, how I should call it, continuously, just after one after the another. One after another, I don't know how to better say it. After another, okay? Yeah, let us be our proposition A, and as I say, it's unknown and probably unknowable, right? So the only way to know is that it's true, it's somehow calculated. And then we, of course, come to some, again, kind of philosophical question, if you like, right? Because mathematically, we really think about this series as infinite, whatever this means in mathematical sense, infinite, right? However, it's clear that, say, some, however powerful computer we use, the kind of length of such a series is limited. It's limited physically, it's limited, if you like, biologically, right? Because we are talking about, there should be some human who follows it. It's not just a kind of process in a, I don't know, in a galaxy somewhere, right? Those are symbols perceived by some intelligent mind or something, right? No, anyway, on all accounts, it's finite, right? But while mathematically it's infinite, and if we making such a proposition, it's actually referred to this, it's a mathematical proposition, right? So it refers to this mathematical reality, whatever it is, right? So it should be somewhere just beyond the reach for any intelligent creature in our universe or something like that, right? Mathematically, why not? Right? So we really don't know whether it's whether A is true or not, or false, okay? And moreover, it's probably not knowable. No, that's kind of, again, philosophical question, whether it's possible to know in principle But the answer is a kind of simple answer is that, or short answer that what is in principle possible, once again, that it just occurs when one does a lot of computation, right? However, to give a general argument that it's just not there is the argument just impossible. No, it's again, it's kind of strong statement. Okay, however, now consider this law of excluded middle. This is the reason why. A or not A, where A is this, as I just defined, right? So either it's there is such a fragment in decimal expansion, or there is no such fragment, right? And again, if you just look, if it's like either, I don't know, you have 100 rubles in your pocket and you don't have 100 rubles in your pocket. So it looks simple. However, in this context, it's already less simple, right? So you want to say, okay, so again, there is certain argument that you may defend excluded middle, even in that case, right? And then your line of argument would be something like, okay, we may not know it, right? But it should be still true or false, right? Because it's a well-defined procedure. It's how we, so when we compute these digits, we kind of come to knowing them, right? It they may be in some mathematical sense already there in some, Platonic heaven. So it should be just the case that either there is such thing or no such thing. And even if it's not knowable, or at least what I just said, right? We might know A, but we may not know not A, etc. It's still, we should stick to law of excluded middle. This is just one line of argument. But the other kind of opposing line of argument would say that, look, we want to talk about propositions that we know, right? We don't talk about some abstract propositions that we never know. It simply does make sense for us. That is called, so people who do accept law of excluded middle, they are said to make classical logic. I actually don't like this word classical because it's just so much, how to say, overloaded and used for so many things. But that's so-called classical logic. So classical logic is a logic that does use of excluded middle. And by the way, all this thing about truth table, it only works for classical logic, right? No, we just checked that, say, this double negation works with truth table. And so that refers also to classical logic. In our case, it's classical propositional logic. However, people who accept and want to follow this second line of argument, right? They are said to prove, to follow, or to use so-called constructive logic. It's called constructive. And it's also called, okay, for reasons that I probably will not going to explain now, intuitionistic. That refers to what intuition. Theonistic. That's because of one important mathematician. His name was Lutz, and then some other Brouwer, who actually proposed this big program of revising all mathematics just on the basis of this construct, without excluded middle, because he just thought that that is not a valid principle. What we do prove using excluded middle is just not really proved. That was Brouwer's view. And he had some kind of philosophy behind it that referred to Immanuel Kant and intuition. So I may probably explain this another time in another course on philosophy of mathematics. but now I only say that it's called intuitionistic logic. That is even more often than constructive, because constructive is sometimes understood more broadly, and there are some versions. So, but key thing is about excluded middle. All right. So, and for intuitionistic logic, these truth tables do not work. And if you want to make semantics for intuitionistic logic, you do some different things. No, again, I don't have time to explain that. One very, how say, popular construction, exactly, it analyzes this in terms of kind of stages of knowledge. So no, it's still logic when it's bivalent, so you have truth and false, but in a sense, you may many things in between. No, it's like for this A, right? We may say we simply don't know it's true or false, right? So it's not this bi-evaluated as true and false. There is something else that we say something in between that we would say we simply don't know. It's true and false, and in some sense, it's also incorporated in this semantic for intuitionistic logic, but it's more involved construction. So I'm not going to develop it now. However, we do develop kind of intuitionistic reasoning, and now it's actually advantage to study logic not in terms of semantics, as people usually did, before computer, no, until recently, I would say, but in terms of rules, because with rules is easier. We just, we kind of leave out one rule, and we have intuitionistic logic, and we add this rule, we have classical logic. So in this Ganson style approach, we may easily to kind of play between these two logic and think about their relationships. On semantic level, it's more difficult. Okay, yeah, you may Google him, read about. He's a great mathematician, very also important as logician, but he also tried to be philosopher. I don't think he was a very good philosopher, but he was one who had a very strong philosophical motivation behind his mathematics, when he said this, right? And so he also remained very important figure of all this story of, say, foundations of mathematics, of early developments in logic, and so forth. So just may Google and read more about him. He was Dutch, by the way. All right. Okay, but now let me just give one more example. So that was my first example with decimal extension of pi, and but there was no really reasoning, right? So that was an example showing that somehow if we have this particular proposition, then this principle of excluded middle does not look as say plausible as with some other usual examples. However, now I give you example of really, say, mathematical proof, which does use, it's a little bit more involved, but I hope you are prepared. There's nothing really difficult. And that's going to be example of reasoning that use law of excluded middle, or this real reduction ad absurdum, if you like, and which is also kind of not quite plausible, not quite satisfactory. No, at least this is an argument. Okay, yeah. So my second example. Yeah, that's example will be example of a proof of the following, say, statement. Okay, you may call it theorem. Okay. And this is the following. There exist two irrational number. So it's important now to remember rational and irrational number, but I think I just recalled you, right? So, but if you don't understand, just ask. To irrational number, numbers, say A and B, such that A to power B is rational. This is the statement. Okay. This is a no. I don't want to call it theorem, because theorem is something which should be true, and this, okay, something that's not quite true. So let's just call it proposition. Proposition. Okay, and now I'm going to give you a proof. Okay, and proof is this. Take A equals B, so equals square root of 2. Okay, that we just came across. Okay. Now, and now we should A to B. So I can see the square root of 2 in power square root of 2. Okay. And okay, and now I'm saying this. Let's call it C. Okay. No, this is a kind of construction, if you like. Okay. Now, I consider case 1, and I don't know actually it's rational or irrational. You see, it's not. You remember still to prove that square root of 2 is irrational, right? We needed some reasoning. We used geometry, arithmetic, so was something in it. But we don't know immediately how to do this for this creature, right? That's more complicated, of course, than simply square root of 2. So, but what I do, I'm going to make kind of trick. So I just consider cases. So I say case 1, when C, when C is rational. Yeah. If C is rational, and then we are done, right? Then there is a this square root of 2 to square root of 2 is C, and C is rational, and so we proved our theory. Yeah. And then no, I would, in mathematics there is this symbol of this black square means end of proof. It's not real end of proof actually, but the idea is that in that case we are done, right? In that case we just gave a good example. But we also consider case 2, because we did not really prove that C rational. We just consider this as one possibility. And the other possibility is that C is not rational, or, which is the same thing, irrational. Okay, this is the other case. Okay, since C is irrational, we can do the following. Consider C to square root of 2. Okay? So what I want to do, square root of 2, square root of 2, and this whole thing again to power square root of 2. Yeah. Who knows how it computes? Yeah, try to compute it. How you do if you have a say A to B and this whole thing to C. Who remembers? Then it's actually equals to B times C. Huh? That's from school algebra. Okay, you don't remember, no? Yeah, but in our case, that means that it's square root of 2 in power square root of 2 times square root of 2. And the square root of 2 times square root of 2 is what?
Is 2.
Is 2. So we have square root of 2 square. And this is
Also 2.
2. And this is rational, right? And so again, if C is irrational and square root of 2 is also irrational, that we know, we proved, right? So again, we have example when we have some irrational number to power some other rational number, and the result is rational. 2 is rational. Yeah. So we proved the theorem. The end of the real end. Yeah, that's probably I should somehow. Probably I should. I don't know. Yeah, probably I shouldn't write really end of proof here because it's not. But let me make square like this, for example. It's kind of provisional end of the proof, right? Now to repeat again, I have two cases, right? I took this a and b some particular value, even the same value of square root of 2, right? Then I had to consider two different cases, 1 and 2. And then in first case, where C is rational, then we do have example which proves our theorem. And in the second case, when C is not rational, which is irrational, we also have example, different example, but anyway, where one irrational, namely C, to power another rational, which is square root of 2, and that gives us rational number 2. That's so I don't know if you have any, how to say, comments on this reasoning. Yes. Is it everything fine, or you feel something goes wrong? Yeah. But this is not a stupid trick. That's not kind of, you know, example where I'm making a stupid mistake and then you say, okay, find the stupid mistake. That's not stupid mistake. It's a really deep problem, but not stupid mistake. So. No, I don't know. No, let me. What you probably may find problematic in this reason, or you know, that's the question. Or no, I understand you don't have so much experience with mathematical proofs. Even it's easy, you see, there is no complex mathematical construction, whatever. It's more like a logic, if you want. You see, but no, okay. Or someone wants to say what it's not just wrong; it's problematic. You see, because in a certain understanding, this is okay. There is no just, you know, kind of mistake. However, there are kind of you know, objection. No, okay, let me tell you myself. Objection is that you see what really happened when you say there exist two numbers a b such that a to b, a b are irrational, but a to b is rational, right? So what you expect is really two numbers, right? which are provably irrational, just as square root of 2 is provably irrational, right? And we studied this proof, okay? And then somehow you calculate A to B, and then prove that this number C is rational, or by direct calculation, by some say indirect argument or whatever, but you have it as rational. But it's not what we do in this proof, you see. So okay, we take this particular value for A and B. We do know that. So somehow we really justify the condition what is given to us, right? That two irrational numbers. So we take concrete example of pair of irrational numbers which are actually the same number, square root of 2, and we do know that square root 2, and we can prove it that square root of 2 is irrational. Okay, but then something strange, or say more questionable and problematic, that is going on, because we still don't know, right? This number square root of 2 square root of 2, we did not study it really mathematically, right? We still don't know, and should be an answer. And I think as I read, it was proved, I think, that it is irrational after all. But it's not easy proof, you see. It's much harder to prove than just square root of 2. But thing is that in this proof, we don't even try to do that, but we just use logic, if you like. And actually what we do use, if you look more precisely, we use excluded middle, but not about this proposition, but about this other proposition, right? That let me call it, say, A, and A is this, that C, as here, right? That C is, say, rational. Okay, let me call this proposition A. And then when I talked about this reasoning by cases, what I actually did, I assumed that it's either true or false, right? Case 1 that is true and case 2 is false. So what I assumed basically that if I take either A is true or not A is true. And this is what I used basically when I talked about these cases. So I say either C is rational, then blah, 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 and we are fine, right? We are done. Or it's not A is true, right? C is not rational, then we have case 2, and again, blah, 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 and we come to desired conclusion. You see, so if you like, here we used what we just came across, this eliminating disjunction, right? So you see that could be used as an example. We have the disjunction like this, A or not A, and then we come to the same conclusion, which is this, that exactly our prop, right? So I can put it here. Yeah, let me maybe even use another page for it. So let me rewrite. A just tells me that square root of 2 square root of 2 is rational, right? This is my A. Is right, you know? And then how I reason? I reason by cases, as I said, right? So I took example, then A is rational, and then it's immediate, right? Since it's rational, then it follows my, well, let me call it P, right? My theory that there exist pair of numbers, blah blah. This is my P, right? Then but I don't know. Yeah, I cannot really use this as an assumption that it's rational because I don't know it's rational or not. And then I take another case, as I called it, that not A, that it's not rational. And then I use some different reasoning, right? But I came to the same P, that again, there exists a pair of such numbers. And then actually what I wanted is to derive P, right? But if you look, what is missing here is missing the disjunction. So what I need to make it into valid reasoning, I need this disjunction, which is A or not A. Otherwise, that simply doesn't follow. By the way, does not follow. It's also logician like to say it in Latin, and in Latin it would be non sequitur. And that's, if you say something, okay, this, it follows. And if someone, your opponent, would say, no, it doesn't follow, it says non sequitur. Okay, and so we do need this. It's not even, how to say, it's actually the single assumption, because here those are discharged, right? As you remember, right? So we kind of assume this A and on A all our disjunct as a hypothesis, but then when we do this inference, we discharge. And this whole rule was elimination of disjunction, right? So it's the injunction elimination. But we do need here this, and this is our law of excluded middle. No, you may say more. At least this is law of excluded middle exactly for this special case. But anyway, right? And that's, of course, no. Okay, this whole example just illustrates that law of excluded middle is controversial, right? Because in this particular case, this reasoning that I just said, it's okay. So if you do accept this law of excluded middle, which is actually equivalent to this rule that the author calls RRA, right? Reductio, no, RAA, reductio ad absurdum, then we are fine. Then we are fine. There is no mistake, right? There is, as I just told you, there is no stupid formal mistake. It's not the case. However, as I just said, that there are kind of serious mathematical reason for saying that that's kind of logical trick. You see that it's not what we want really in mathematics. That and this is this so-called constructive viewpoint, and that's why it's called constructive, right? I'm probably not explaining intuitionistic, but I may explain where this name of being constructive comes from, right? Because you see, we proved it without really giving example, because that's not a real example. That only, how to say, it's not example, because we still don't know whether it's C is rational or irrational. But we somehow, using this included middle, we went around, right? We still prove the theorem without really giving examples of such A and B. And now there is a kind of serious logical choice and principle choice that some people say, okay, we still do accept to do mathematics with it, right? It still gives us, sufficient logical foundation, important new results, and so on. But some other people say, no, we just don't want to do mathematics like this, right? We do want mathematics when you say there exist two irrational numbers, show us these irrational numbers, you see, and make your calculation that really proves that first that A and B are indeed irrational, and second that A to B is indeed rational. Yeah, and here we don't have such. All right. So, But then, of course, some, more, I don't know, disengaged party would say, okay, let's just do two different kinds of mathematics. Just let some people do classical mathematics, some other people do constructive mathematics. Okay, or maybe just it could be the same person who does, say constructive mathematics on Thursdays and non-constructive mathematics, I don't know, on other days of the week or something like this. But anyway, even if we don't decide, I don't know, philosophical in some ultimate sense, whether this excluded middle is valid or not valid, it's still, no, at least that's my take on all of this. It's still good because we have a control. You see, we understand what we are doing. It's here we do use excluded middle, here we do not use excluded middle, and then okay, we produce certain results with excluded middles or the other without excluded middle. Okay, and actually coming back to my first example, you may kind of feel, I'm not going to give a precise argument, and probably does exist even, that this constructive mathematics is actually very much related to computer science, right? So roughly what we do in computer science, what we do algorithmically, it's in a sense all constructive. You see, no, except of course that we may, in a sense, do both. No, first of all, we may also implement classical logic, right? We may kind of implement excluded middle, but it will be less direct than we may implement all other kinds of reasoning, right? And but we may also say when we calculate pi, right, and we say that we approximate pi, you see, we kind of do both. On the other hand, we have this kind of non-constructive object. No, that's a little bit different than not constructive argument, but anyway, like transcendental number pi, right? And of course, the one who is really constructivist may even take this view that such numbers do not exist in the sense that do not make any sense, right? That only numbers which kind of mathematically approved are those that we may calculate in some sense, or yeah, no. So there is then there are of course many positions whether we should say also limit, say, length of our calculation just by saying that we have some limited resources, we live like life is finite, right? The universe is finite, everything is finite. Or we may still accept, even in constructive mathematics, this idea that we may calculate as long as we want. But in our case, that doesn't really help, that if we may calculate as long as we want, because what we really want for justifying classical reasoning, that somehow say truth or false is in advance. So we may not know what it is, we may not know whether or not there are 100 zeros in this decimal expression, but it's somehow either true or false. It's a different question whether we know it or do not know, right? But constructivist people say that since we do not know that and even cannot know it in principle, then it's just pointless to talk about it. Yeah, but then there are many more nuanced positions and many interesting things. Okay, so I think if you have any question to this part, just on these examples, all this was to illustrate, to show you the difference between so-called classical and say constructive or intuitionistic reasoning, right? And somehow explain the idea and differences. Roughly speaking, there are more nuanced notion of being constructive. I just explained you very simple, very basic. So different is whether or not we assume low excluded middle or in some equivalent form like canceling of double negation, or in this form of rule, as we have in our textbook. So issue is whether we accept this as a valid principle or valid rule, right? And I showed you that at least in some contexts, it looks uncontroversial, right? Like A or not A. But in some other mathematical contexts that I just introduced, it appears to be controversial, right? And that's why actually logicians do both, do classical logic and also non-classical logic. And this non-classical just includes everything which is not classical. Let me better say constructive, right? And constructive logic is particularly relevant to, say, computer science. It's not precise statement, but I think it's true that far. Okay, so we in this constructive logic we do everything we may really compute. Okay, yeah. So if you have any question on that stuff.
Actually, thank you for explaining again, because when we were discussing it for the first time, I got kind of lost, but now it's clear.
Okay. Yeah, it's better to go several times, that's sure. Yeah, already, did I already explain this square root of 2 example, right? Did I remember that I mentioned this, but I can't remember if
no, I'm talking about when we just started talking about it today.
Okay. Yeah, I think I mentioned something in the beginning about it, but yeah, now it's no. Okay, let's now probably go back to this textbook. So what they look, I should go again to share. Okay, now it looks a little bit bizarre. What do you see now? Yeah, do you see back the textbook?
Yes.
Yes.
Good. Yeah, no. So just back to this rule. That's the rule. That's the rule, which, as I explained, is plenty and which is more controversial than other rules. But that's, I think, that's the last rule that we have as basic rule, right? And then, as I just explained, we may introduce more rule by combining those rules. Okay, then they talk about language of propositional logic, but basically I explained, I think, already language. No, language consists of these propositional variables, the symbols for logical, say, operations, right? That's and also, say, brackets or parentheses, so call them. Yeah. Well, okay, there are some little, I think it's nothing really. Yeah, some of these exercises we did already, right? And so they were actually asking us kind of translate between this formal language and normal English. Yeah, and then it's basically they do the same. But now let's see what we can actually do with all this and make at least some simple exercises. No, yeah, that just shows it's not very interesting example, but they just show how these rules may be combined, right? So we have this introduction for conjunction, right? And you see we use it twice, like in parallel. So this kind of diagram, it's actually called a proof tree, как дерево доказательств. Yeah, because if you can let me maybe try to show you. Sorry. Yeah, you see, so you here is it's like a root of your tree, like корень дерева, and something goes wrong. Yeah, and this is basically what you want to prove. So it's kind of upside down, you see. On the bottom, it's what you want to prove, and on your branches, there are kind of your premises and how you move, and this is a kind of parallel. So in that case, you just start with actually three premises A, B, and C, but this premises A is repeated. You see, so you use you introduce conjunction for A and B, so you obtain this conjunctions A conjunction B. Then you use the same for A and C, right? And then you use once again the same actually rule for conjunction, but now you make this longer conjunction, which is A and B conjunct A and C. Okay, that's not very interesting example, but it's just shows how you see how it works. Yeah, and okay, here is something a bit more interesting. It's basically the same example. Okay. Sorry. I just want. Okay. It's you see, you may actually not stop here. Here you stop, right? You just use twice the same rule. But now you may also use you may also introduce implication, right? And in that case, you discharge your hypothesis B. That means that you see here your reasoning depends on A, B, and C, right? So in terms of truth value, if A, B, and C are all true, then what you have on the bottom is also true. This longer and kind of two-leveled conjunction is also true when A, B, and C are true. But then you introduce, using this rule for introducing implication, you introduce implication, and now you discharge this hypothesis B. And that means that this is true. Now, B implies blah, blah, blah. When A is true and C is true, but you should not any longer say B is true, right? Because it's discharged, you see? But then you may, in the same way, actually, it becomes a longer formula, but basically you may discharge all those hypotheses, you see, and it's kind of a series of three implications, and you discharge all those hypotheses, right? That's example, not very, yeah. Yeah, but that's interesting special case, you see. In fact, we can also carry out the implication introduction rule and cancel zero hypothesis. For example, the following is a short proof of A implies B from the hypothesis B. So, yeah, so that's also valid rule, which is considered kind of special case of this rule for introducing. So if you have just B, right, you may also introduce whatever A. It's a little bit like with disjunction, right? If you have A, you may introduce A or B. And now if you have B, you may introduce, so you may infer A implies B for whatever A. Yeah, and now there are all these rules I already showed you in the beginning of our class today. All those rules are summarized, so you may just look on page 18 or not 19. It's the next page, and then you have okay, for implication, for conjunction, for negation, for disjunction, no, truth and falsity. So you may introduce truth whenever you want, and you may that we discussed, like ex falso quod libet, right? You can deduce whatever you want from contradiction, from falsity, right? This equivalence, they call it by implication, but that's the same that we came. And finally, this reductio ad absurdum, right? Now, let's look again to some examples. Right, yeah, that's different example. And then probably next week we'll do some exercises. And actually, I ask you to do as a homework, and then we do them together. Okay, now we want to prove, yeah, A implies C from A implies B and B implies C. So you see, it's a kind of what in mathematics we would call transitivity of implication. No, yeah, I think it's kind of intuitive, right? I can, let me write it that way. So, yeah, so I have A implies B, okay, and I have B implies C, okay, and so what I want to prove that I may actually compose these arrows. So that's given this, actually A implies C, no, which is plausible, right? If we still think, I told you, you should not think about implication as anything like inference, and actually relationships between implication and inference are treated by this first pair of rules, modus ponens on the one hand and implications of introduction on the other hand. But anyway, if you still think about it, if you still do that, right, that means that, okay, A implies B, B implies C, and that means that A after all implies C, right? But here is a formal proof how we do. So we want to prove, right, so we have right, so what is given, it's just these two hypotheses, A implies B and B implies C, right? So how we proceed, and we don't have an immediately rule that would involve two implications, right? And do something with two implications. We don't have such a rule in our list of basic rules, right? But what we do, we assume also A as a hypothesis, right? So we do use A implies B, that's premise which is a given. So we entitled, you may think it's whatever, axiom, but it's given in our exercise, right? But this A we add up as a hypothesis, and then we see we can make modus ponens, right? A implies B, we add A, and so we conclude that B by modus ponens, right? And then we do have B implies C, also it's our data, and now we have B, and B implies C, so modus ponens once again, and we conclude C, right? And from C, as I just explained, we may actually, no, basically what we got, we, you see, we have this pattern of introducing, or pattern rule of introducing implication. So we started with the hypothesis A here, right? We did some reasoning using our rules and using our data, what is given, and we came to C. And at that point, we introduce implication and discharge our hypothesis. And that was yeah. So we use at that last step, we use what? We use this rule, right? That we started with A. No, then we had C, not B, but anyway, we proceed, and then we introduce implication and discharge hypothesis. And it was important to discharge hypothesis. Why? This is because we are asked to make to present the proof, to build the proof of A implies C from these two data, right? A implies B and B, and A was not among them, right? We added it up. We added A, and that means that if we edit it, that means that at the end we should somehow get rid of it, right? We should cancel or discharge it. But that's exactly what is done. What this rule of introducing implication allows us to do. Yeah. So I don't know if. Yeah. What we can do once again, it's just mark rules which are used at each step. So we have one step, right? Second step and third step. So let me ask someone. Once again, I told you, but please someone volunteer, repeat. So first step is which rule? And I mark it here. Which rule is first step? You may look into your list of rules. Nobody? So to which horizontal bar is a step, is a logical step, right? Is an inference, semantically speaking, or derivation, syntactically speaking, right? And each such derivation is a subject to certain rule. And those rules here are elementary, so they are in our list of let me call them elementary rules, not fundamental, whatever. Elementary, I think that's good word. Elementary. So who can say that's upper bar? Which rule it is? Silence. Yes, please.
It's implication elimination.
Yeah. Otherwise called modus ponens, right?
Yes.
Yes, exactly. Yeah, but let us call it the implication elimination. You are right, because we are in. So it's. I would rather write not just E, but something like elim. Otherwise, it's not. Yeah, that's first. Second. Yeah, let someone else.
Okay.
Yeah. Please. What is second? Here I can also call it modus ponens, right? It's just different name for the symbol. Whom I can ask? Vasilisa. Can I ask Vasilisa?
So.
Vasilisa was the same. I'm sorry. Yeah, no. Then I ask Diana, for example.
Okay.
I'm still thinking.
Yeah. Or Valeria. And what about Maria Loshkina?
It also seems to be implication elimination, no?
Yeah, it's the same rule, exactly. Right? Oh, sorry. What should I do? Sorry. Sorry, because Yeah, that's correct. What about the third one? Yeah, so here I write also implication elimination, right? And I can number them, right? Because that's just number of steps. It's not always easy to number because they may also go in parallel. That's rather involved. But in that case, it's like consecutive. There is no parallel. So that's also implication elimination, right? And the last one, please, someone. It's also implication, right? Okay, let me ask. Arina, probably I didn't ask Arina. Arina, can you hear me? Probably not. What about Ivan Lazarev?
Honestly, I don't really know.
Okay. What about Sofia?
I think that's implication and elimination too. No?
No. It's implication, but not elimination, but introduction.
Oh.
Yeah, it's introduction. Let me explain it once again, and then we conclude. Yeah, because once again, no, first of all, you see above the bar, you don't have a implication, right? And below the bar, you do have, so it couldn't be elimination of implication. So there, it was the opposite. We did have implication above and no implication below, right? And second time also. But third time, it's the opposite. We don't have implication above and we do have implication below. So it's introduced. So it's a introduction of implication. But now let's see again more precisely why, how it. Let me see back again to this rule. Okay, let me just write it down here. Yeah. So what is the rule for implication intro? It's kind of diagrammatically, it's like this, that we have some A, right? Then we have these dots which correspond to some reasoning according to the same rule. As I told you, it's kind of circular, right? Self-referential system, but it is like this. All right, then we see, and then I just mark this A here, right? Because that was our hypothesis. This premises like A implies B, B implies B, they were given there here, you see? And A was not given. It was our hypothesis that we actually need to discharge. So I have this A here, and I do actually implication elimination twice. This is what I do, right? Using my data, right? And finally, I conclude C from this A. That's what I'm doing. And then I introduce A implies C, right? So in a sense, I replace this reasoning by implication, you see? So that's exactly what gives you relationships between inference and implication. And of course, they are kind of related, right? But in this precise way. So it's not the same thing, just saying that A implies C in the sense that you infer C from A. No, but if you do infer C from A by some reasoning, however complicated, right? Then you may conclude A implies C, and what is very important here, you discharge A. And they write it that way. And when you have many discharges, then you should somehow understand where, how say, by which rule you discharge which hypothesis, and that's why they put the small number, just to keep track. Now here it's just one case, and no need in a sense to keep track, but yeah, or rather you put this little one here, because that refers to inference. You're making this inference, and that allows you to discharge hypothesis, you see? Right, so it's an introduction. So two times you eliminate implication, but that is what you see, what was in the beginning. You had to prove that A implies C, and what was given to A implies B and B implies C, right? So you had to eliminate these two implication and introduce this one, because it was not given, it was something to be proved. Okay. No, I don't know. We look for one more example, or we finish. I may look for another. We started a bit later. So how you feel? To the end of my class, you kind of become silent, and I'm really become worried about you. Are you okay?
No, we're here.
Yeah.
I
So
guess we're just processing all the information.
yeah, I understand. That's no. Now we come to kind of real thing, right? So I explained a lot of background and the rules, etc., and now it comes to real examples. So yeah, probably I do this undo. I can just clear all drawings. Wow, that's it. Okay. Now let's try one. No, okay, one general remark also about these rules. It's something I told you, but now you can kind of see this more practically. Is this these rules are not algorithmic? You see, not algorithmic in the sense that they don't tell you generally what to do next. What is your next step in reasoning? It's rather like you are driving a car, right? And you should drive according to rules, right? No, it's a bit more strict than driving the car, because driving the car, you should not violate rules. Here it's more strict in the sense that you should really follow rules. However, not just violate, but just follow. However, you have a set of rules. It's not just one rule, right? If you would have one rule, you would just repeat it and would be very poor as a, you see, as a deductive system. But you have actually some number of rules, and you may combine them, right? You may apply one after another, and what you obtain as a conclusion, you can use as a premise for next rule, and that's exactly what happens here, right? So we obtain B as conclusion, but then we use it as a premise for the next inference, right? And again, we obtain C's conclusion, and again use it as a premise for next reasoning. Okay, but that allows you actually a lot of freedom, right? So you may apply this rule or that rule. So it's no, it's more like a game of chess in that sense, right? That each move in chess is according to rules. If you're a horse, it should go that way or this way, and it's every time according to rule, right? However, you have a lot of possibilities, right? This game doesn't tell you what to do next. What is your next move? This is up to you to think about this and to choose. And this is how this formal deductive system works, you see. And for example, that means that if we want to write, to use the system to write down somehow a formal version, say, of mathematical argument or mathematical proof, right? It's does not help you really to find this proof. You see, it only helps you to codify, to make it not just informal, even in mathematical sense, but really formal. And actually, what is done, if you really manage to implement it now in computer, then you may implement your proof on computer. But again, that wouldn't mean that computer would prove instead of you, right? And it wouldn't even mean that computer would find the proof and you kind of consume it later, right? It wouldn't find the proof, but it will be a proof which is verifiable, right? You can kind of run this proof and see that it holds at the end, right? That it computes, and this is how it's used in proof verification. And that's another issue of actually finding a proof. And there are also work on this, but that's a completely different issue, actually. Yeah. And then you use more like machine learning, this kind of things, which are very different from what we're talking about. Okay. Yeah. No, I propose the following. So as a homework, look at this next example. You see, it's longer. I think if you start now, everybody is just too tired. Yeah. So yeah, just look next example. And probably also this forward backward reasoning. But then and also remember, I asked you to prove that's another homework, that double negation and law of excluded middle in the form of A or not A as tautology are equivalent. Yeah. And third thing, it's more complicated, but just look on this rule of that they call this rule. This last reduction ad absurdum. You see, it's kind of self-standing. It's not introduction or elimination, self-standing, and also think in which sense it could be also called equivalence to law of excluded middle or double negation elimination. No, with double negation elimination, actually, I already showed you, right? If you just consider this as a instance of introducing negation, right? Then you get here in conclusion, instead of A, just not A. And for saying that not A is the same thing as A, you need again this additional principle. Yeah, so we may next week discuss how these different forms of law of excluded middle, how they relate to each other, how they translate into each other, right? And then we'll just do more examples, and yeah, and then probably we switch to a different topic. Okay.
Okay.
So if you don't have questions, if you do, ask me. If not, then see you next week. I'm sorry for being late today. Now I know the difference, so I start in time. Okay, have a good week.
Thank you very much.
Thank you.
Thank you. Goodbye.
Thank you. Goodbye.
Goodbye. Goodbye.